we will not go into all those facets, but we will concentrate on snow and glacier melt, how it is done by considering the various aspects. So the modeling process is started much early in 60s, much earlier than that, where basic idea is to find out uh, how much is discharged into the river. So there are various ideas where you can. One of the earliest idea, and which was until very recently in Himalaya, it was used. You use the drainage area and precipitation to estimate the stream flow. So you can simply correlate the amount of precipitation and then try to correlate it with runoff. That is indeed a first level of first approximation, and early 50s and 60s people have used this to estimate the stream run. However, that idea that when you have a high precipitation, at the same time you will have runoff, may or may not work if you come into the cryosphere region. So this is a picture, if we can see that, where the runoff and precipitation are plotted. So whatever you see red here is the precipitation, and you can see the precipitation very large in March, but runoff is, which is blue in color, which is very low in March. So what really happens is, even though the precipitation is reduced, runoff is start increasing. As summer comes, precipitation reduces, but runoff is also increasing. And then, of course, then there's the monsoon time when precipitation is large and runoff is also large. So whenever it comes to snow and glacier melt, there is no one-to-one relationship between the precipitation and runoff. And obvious reason for this is quite obvious, that snow melts later on, and it depends upon temperature. So that is more thermally controlled. So if you really want to have a simplest, what is the idea, simplest idea of any snow and glacier melt runoff model is, first of all, you need to estimate the melt water. How much is melt water is there? And then once it is melted, then the effect of drainage processes on this, that means some of that water will be used into infiltrate into ground, or some that will be used in increasing the soil moisture, then it will go into evapotranspiration. Numerous processes will take place on that, and then there is a runoff. And at the end of the day, when you are doing the runoff, it is not only estimate of melt water, but you have to consider the principle of conservation of mass. What it means is that we cannot produce the runoff which is higher than whatever is water available in the basin. So we require a water balancing. Other way you say it is a water balance. So this idea has to inbuilt into the model. You can build your own model, or you can use the existing model with different processing. So let us first understand how can we estimate snow and glacier melt. If you look into the equation of that is the energy balance equation, to begin with, it is very easy. Essentially because the melt, or M in this case, is the melt water equivalent, is a function of energy flux available for Qm, which is the energy flux available for melt. The HF is the latent heat of fusion, D is the density, and B is the thermal quality, or the fraction of ice in unit mass of wet snow. So snow is wet. As we are discussing, how much is a water in it and how much is in uh, ice in it. So it is a fraction of ice in unit mass of its snow. So if you have this thing, then we can simplify this equation where Qm divided by, you know that latent heat of fusion and density of water. So you can use by B. So there are only two unknown parameters in this is energy available Qm, which is energy available for melt, and B is the thermal quality or the fraction of ice in unit mass of snow. You can also estimate that fraction of by if you know the density of ice or snowpack, density of snowpack. If you know it, then you can know that how much is there. So key question is QM, about which we were talking about. QM is amount of energy flux which is available. So energy flux have different components, and we must understand that. We will not go much detail into this, but for you to understand it, and many of you may be aware that QM, which is energy flux available for melt, which is which is depends upon short wave radiation flux absorbed by snow. That means how much is short wave radiation flux is available, and it is incoming from sun, how much it is absorbed, which is absorbed by snow. So here comes the albedo is, or a reflector, whatever way you want to characterize it. So it is how much it is absorbed by snow. So the long wave radiation flux at snow and ice interface or snow and air interface. Then there is a sensible heat flux. Then there is a latent heat flux and flux from ground, snow and ground interface. That means we have seen that snow is a bad conductor of heat, and because of that, there is some moisture energy transfer from ground to the snowpack. So that is flux from snow ground interface, flux from rainwater. It is quite possible that snowpack receives the rain, and depending upon the temperature of rain, it can really enhance the melting and so. And then it is how much is energy used to change the internal energy. That means what happens is if snow melts at the surface, as it passes through the snowpack, it's quite possible that snowpack has much lower temperature than freezing, and then that is water is refrozen to and gives the exothermic because of the freezing, and it internally increases the temperature, and this process is important till entire snowpack becomes isothermal. That means it comes to the 0 degrees Celsius. Until such time, these processes are very important. So that is how energy exchange is all about. So there are different methods to estimate the snowmelt. The energy exchange is one method. We will not go into detail of that as of now, but there could be a separate talk on that, but today we are not going to take it. So another idea in this is, instead of, because it is generally very difficult, if you really go into the previous figure, if you want to know latent heat flux or sensible heat flux, you require the wind, a change in wind, you require humidity, so many other parameters are required, incoming shortwave radiation and the outgoing shortwave radiation. So all those parameters are generally not available in Himalayan terrain. And because of that, it is very difficult to apply this model in Himalayas. But now there are a lot of satellite data is also available, so probably you can use some of those ideas. But then what? Otherwise, people have tried to use temperature index. That means a temperature is considered a proxy to all energy exchanges, and most of the operational models, if you use any hydrological model, they use the temperature index, where the degree days are determined using maximum and minimum temperature. I think today you will do that exercise. So you will understand how degree days are calculated. So you calculate the degree day and with this T maximum plus T minimum divided by 2 is taken and the T minimum is less than 0, then it is equivalent to 0. That is essentially to make sure that it is not really, there is some melt takes place because of the maximum temperature, and when night becomes a minimum temperature below freezing, they should not cancel out each other and it model will show there is no melt. So to avoid that, um, so it is wide, it is available and it is reasonable. T temperature is a parameter which is generally available in all observatories and it is a relatively stable parameter. Therefore, you can get the good estimate of temperature in various altitude zones. What it means is that you can estimate the spatial distribution of temperature far easier than many other parameters which requires, energy balance. So in that sense, it is much simpler, therefore it is quite popular. But key question is how do we do it? Essentially, because the melt, if you really look in terms of melt, because you have uh, temperature index and certain degree days you have estimated, but you need to convert that into the melt because it is only proportional. You can argue that temperature is proportional to melt. It is not because we have seen there are so many other parameters. Because of that, we require certain proportionality constant there to estimate the. So it is normally M melt water equivalent is equivalent to melt factor uh, into temperature index. That is how that relationship is developed. And what is the melt factor? There are different ways by which you can estimate the melt factor. And melt factor will have parameters such as vegetation transmission coefficient. That means for radiation. So how dense is a vegetation? If you go into the high altitude region, then there is no, it is vegetation transmission coefficient is 1 essentially because there is no vegetation in glaciated terrain or high altitude region. But whenever there is, if you are looking into the winter and spring runoff, you can see there will be a snow below the vegetation cover and you require to do that. And then solar radiation index and the albedo of snow. So a solar radiation index and albedo of snow, these are the parameters which change with time and it can change spatially also. Therefore, it is important to add to understand that. So snow is pristine and very high altitude. It is not contaminated. Then it will have very high albedo. It could be contaminated as well. Either it is this particular case, this contamination is possibly due to volcanic ash, but it can be also contaminated because of the mineral dust and numerous other parameters and significantly um, change thing. In addition to that, there is a different albedo. We know that there is a significant change in albedo takes place as snow gets converted into ice. We have seen into that. And it means that there is a different melt factor for snow and ice because albedo has a low ice has a low albedo, therefore it has higher melt factor, and snow has a high albedo, therefore it has less melt factor. So you have to realize it is function of that. When it comes to the incoming solar radiation, it is also a function of various geometry between sun and earth, and it is also, and the geometry keeps on changing with reference to the slope and orientation of the terrain. So it will, in direct incoming solar radiation, you can see here, is a function of terrain azimuth angle. So what it means is that if a terrain azimuth, if you take is a and terrain. So you take the case where terrain is say approximately 50 degrees um, terrain slope, and if slope is 50 degrees, Then there is azimuth, and depending upon azimuth angle, you can see here where is 50 degree. Uh, okay, you take it 30 degrees. 30 degrees, no, we will take 70 degrees. Okay, 50 degrees not plotted. So you take the 70 degrees, and you can see here, if if the slope is 70 degrees of land, and if it is orientation is in northern side, that means certain time of year, suppose you take around 10 o'clock in this morning, then there will be mountain shadows there. It will be under mountain shadow. Only when this is done. So if you, depending upon slope, either and orientation, certain region will be under mountain shadow. And if we change the slope higher, then only when you reduce that mountain slope to 30 degrees Celsius and depending upon the solar element, there will be a incoming direct solar radiation is coming. How much you can calculate that? There are some formulas by which you can do it, and some of these exercises probably you will do it later on. So it is a function of terrain azimuth angle and terrain slope. So incoming solar radiation is going to change from place to place. And therefore, there's a way to model it. You can model it, but what you cannot easily model it. So the relationship between terrain, so incoming solar radiation and solar and sun's position can be modeled. But it is very difficult to model because incoming solar radiation can significantly change because of the cloudy cover and other features, atmospheric features. And they are relatively difficult to model because they will change spatially as well as they will change temporarily also, because clouds may be there now, it may not be there after an hour, and they are random. They are not something easily to do, unless, of course, you use satellite data to do it. So you can do that complex modeling to do it. So the concept now is we have all these parameters, then we know how to estimate melt factor, but we also need to know how the temperature is going to change. And we know that most of the time temperatures are available in station, and which is a low altitude generally. So particularly Himalaya, you can estimate temperature in different altitude zones, and you can do it. Himalayan terrain temperature will change with altitude. So you can do by adjusting. TH is a altitude adjacent of temperature index, then temperature lapse rate, mean elevation of station, and mean elevation of altitude where you want to estimate the temperature. So by using simple relationship, you can do it. And this is a TA is a negative, then considered as 0, and this will give, and then you can convert that TH is a temperature which is adjusted. By using that, you can get the melt. So TA is a negative, then considered as 0, and this will give a melt over a unit area. That's the idea. But now we got it over a unit area, and we want to estimate snow for our glacier melt for an entire basin or a certain geographical area. So in order to do that, generally, people are going to do the, in each altitude zone, you can do it. So how much is basin area in each altitude zone, that you first estimate. Then what you should estimate is how much is snow and glacier covered area in each altitude zone, that you should have that estimate, and how we will ensure that the amount of meltwater produced is not more than total water stored in each altitude zone. So there are three fundamental questions which we need to address. One first question is, how much is the basin area in each altitude zone? Of that area, how much is snow and glacier cover in each altitude zone? And then how much it can produce a lot of water, I can assure you that. But what is the water balance? That means you cannot produce more water than what is available in the form of snow and glacier. So that's the idea. So that is last argument is related to the water balancing, how you are going to balance the water, balance it out, water balance. So first thing is, how do we estimate the snow cover in each altitude zone? The first thing it says is, how do we estimate snow cover? There are different methods by which you can estimate the snow cover, and you can use generally NDSI, normalized difference snow index technique is used, and we have seen band 2 and band 5. AWIF is used for that. Band 2 is a green band, and you can use band 5 with a sweet band. We will have a more detailed discussion about NDSI when we go into the snow cover modeling lecture. We will see when it is scheduled. As of now, it is scheduled at the end, but we might reschedule it with due course of time. So, so you can use that and you can estimate the. So let us look into how to estimate the distribution of snow. So you can draw a simple hypsometry. You can digital elevation model, and you can plot elevation versus area, and you can get how much is in each altitude zone. Then you can use the NDSI algorithm to estimate snow cover for entire basin, then superimpose on that basin your altitude. You can clip within the altitude, and you can get how much is area which is covered under each altitude zone. And you can also know how much is total area, so you can say how many percentage area, whatever way you want to later on use it, you can use into that fashion. But in order to meet the third idea, how we will ensure that that amount of meltwater is not more than total store water. First thing is there could be multiple solutions for this problem. And one of the easiest solution to this problem is if we get how much is depth and density of snowpack. That means we know the spatial distribution of glacier depth. And if we know the density, we can estimate the water equivalent. So if we know the water equivalent of snowpack by various means, either by field investigation or by so many other techniques, remote sensing technique, particularly if you are using gamma ray, scintillometer or other meters, you can do it, or some microwave techniques if you are using. You can know that. If you have that, then it is, then you can quickly incorporate that into the water balance and do it. If you don't have, then what you can do is, you can use the depletion curve is the idea, which is commonly used by engineers in past. Generally, problem in Himalaya is snow accumulation also changes with altitude. So it is not like prairies of North America or a plain region of Europe, where you will know if you have few observations, you can spatially distribute that observation. But here in Himalaya, it is very difficult to maintain it, and it is keep on changing from place to place, essentially because of the rugged topography of the Himalayan terrain. So you can, one of the ideas which is used by people, not necessarily it is very brilliant, it can give very highly accurate result, but it can definitely give you some assessment about how much glaciers store water in each altitude zone. So the idea behind this is that each altitude zone will melt in a different period of the season. That means what you can see here is, you can see here, if altitude range, which is between 2,400 to 3,000, and altitude range between 3,000 to 3,600, you can see here. Here the melt starts in middle of April, but here the melt starts only in middle of March, and by the time middle of May, it is completely over. This region is not contributing, and the region on top is contributing middle of April to the to the end of May. So what really it means that some regions are contributing more in certain times, some regions are contributing more in other times. And using that idea, you can estimate, and if you have runoff data, then you can estimate that how much is the glacier store water there. So that is the idea, which is also commonly used, particularly for those large basins like and they are transboundary basin where it is very difficult to get the data from other part of the world and makes it difficult. So these are the ideas which are used. Not necessarily they are ideal, but they provide you certain clues to do it. So there are, once you have this idea that you know the temperature distribution, you know the albedo of snow, you convert that albedo into the melt, and then you know how to do the water balancing. That means you are not producing more water than what is available. Once you have that clarity in your mind, then there are modeling effort. That means how much is melted and how much it is available at the stream, wherever you want to do the measurement. So there are different modeling ideas we are using that, and this one of the such idea which is very extensively used in past. Now people have moved to some other better models, but you should have some historical idea. It was called Snowmelt runoff model. So this model uses the degree day approach and snow cover extent. The model parameters are temperature, snowfall, and snow cover area. You must be thinking that what made it, why it was necessary for people to develop Snowmelt runoff model. One of the parameters, if you can look here, is the snow cover area. So snow cover area is a dynamic in nature. It means that it keep on changing in season. So it can change in winter time as snow falls, lower altitude will make. In summertime, it will significant reduction in takes place. So it is a dynamic in nature. If you look into the hydrological model, whether you use the SWAT model or WEAP model, basically, particularly SWAT model, it is coming through the land cover. What it means that snow cover is considered as one of the parameters of the land cover. It means there is no dynamic nature of snow cover can be accommodated into the model, and that is why people thought it is not giving very reliable result. Of course, all models are now modified. I am not saying they are not modified. They are significantly modified recently, very recently, to accommodate some of those ideas, or wherever it is not modified, people are trying to use it, include the dynamic nature of snow and glacier cover into the model. So that efforts are still going on in some models. Some models they have used it. So so you can, that is used, and in this particular model, Snowmelt runoff, SRM model, seasonal runoff, where it uses the depletion curve. That the depletion curve and runoff are used to assess snow region and seasonal runoff. So you require two parameter depletion. So what idea in this, you have historical data of snow cover. From that historical data, you estimate the depletion curve, correlate that depletion curve into runoff, and presume that it will remain so in this year. And then by using by using that, you get the seasonal run. So entire season, how much is the runoff is there? You may not be able to get good accurate how it is going to get today, tomorrow, or a weekly basis or daily basis, something like that. But you might get reasonably good result on season as a whole. So if you are really a manager of Bhakra Bias or other hydropower plants, then you want to know in the summertime how much water is going to come. So you can schedule your requirement for agriculture, your requirement for hydropower generation. So reservoir operation, this is very important. And anyway, as monsoon comes, there's a huge amount of water enter into that. So there's another set of reservoir management will take place. So this is for summertime management. This model was successfully used for National Remote Sensing Center, and it is routinely runoff estimates are given by middle of March to the Bhakra Bears management. So this is one of the idea. Idea is in this model is this, that the depletion curve produces the runoff. That means, but in a glaciated terrain, there is no depletion of area. You understand, glacier doesn't retreat on seasonal basis. They respond much smaller. This annual retreat is also very small. You can have significant retreat on decadal scale or a centenary scale. So that is the problem. So the glaciated terrain can significantly produce the runoff without the depletion and without large depletion. So that was a limitation, but eventually I think the model has for very long period, this was the limitation, but eventually it was really some of those issues have been addressed into the model. So having this background, what you will work today in your exercises are about Snowmelt runoff modeling. It is a simple model. I would like to give what was the philosophy behind developing this model. And it was developed way back in, I think, year 2000 or 2001. In that time frame, around 20 years back, this model was developed. But it is a still good idea for you to get when you do the exercise, because to get you hands-on training, this is important. And no matter which complex model eventually you are going to use, the fundamental processes within that are very similar. To start with, eventually they get complex, but start with the similar. Therefore, it is important for you to understand what it is. So, when we prepared a first glacier inventory atlas of Satluj Basin, people were not very enthusiastic about this glacier atlas. That means people thought that what is the use of this atlas, because it is glaciers are lying there. We are talking about early 80s and early 90s time. It's the 90s, not 80s, it is the 90s time frame. The climate change was not very important topic at that time. Nobody, people were still arguing whether climate change is really there or not. So we thought at that time that it's a good idea to use this data for estimation of hydropower of a glaciated, snow and glaciated stream in the Himachal Pradesh. That was the idea. So we had an inventory data at that time, and then we thought that. So we sat for the discussion with Himachal Pradesh government, and Himalaya is the organization of Himachal Pradesh, which is responsible for systematic development of hydropower into the Himachal Pradesh. So we had a discussion on that, and they have said there are a couple of issues in 90s which they were facing. And what are those issues they were facing is Himalaya, they said Himachal Pradesh has a large number of snow and glacier streams, and systematic assessment of hydropower potential of each stream is needed. That means there was no idea at that time. They have a geographical area about each stream, that is basin area, but how many glaciers are there, how snow cover is changing, there was no idea. So therefore, in sitting in a state capital or national capital, you have no idea that each basin will generate how much power or how much steam is there. Then there is a mountain stream has lean discharge in winter. And feasibility of hydropower plant depends upon winter discharge, because you invest a lot of money. So what is the winter discharge of the stream? Because as monsoon comes, there is a huge amount of water is there. So most of the power plant will run properly in the monsoon time, but this winter time was difficult. So they wanted to know how much is the discharge in winter. And therefore, they wanted a model which can assess the inter-seasonal variability in stream discharge. They have another problem, not necessarily we solve those problems, but I think it is important for you to know some of those problems. Himachal Pradesh is, at that time, not necessarily now, is a surplus state of power generation. Summer power generated from hydro station can be sold to adjacent state because still Himachal Pradesh takes power to the Punjab and Haryana. However, the power purchase agreement has to be done in February for summer. So can we forecast the variation in power generation by using previous year? So they want to know in February how much variation in power potential is going to come compared to last year. So how much power they can save to the Punjab and Haryana. That is the idea in that. Not necessarily we have worked on the all ideas, but some of those ideas still valid and some of you can still work. But we are not able to address all of their projects. But there was also one more problem which they face in Himachal Pradesh. There are many uh, uh, mini and micro hydropower projects generating power, and there are a large number of planning. Still, it is there. Many of them have become operational now, and runoff of this stream depends upon snow and glacier and how climatic variation can change glacier and snowfield and how these changes will affect future stream runoff and future power generation. That is something which is added new, but originally at that time there was no that idea, but as we move into the 2004 and 5, this really requirement has also come from numerous power operating uh, uh, companies as well as entrepreneurs who want to have a power station in those regions. So we decided to have a simple model and which you will work later on. Today's exercise, we will work on that to understand seasonal snow and glacier Metronome. So this is the first cut information which is given to the planners it is called pre-feasibility level investigation. So this investigation is done by Himachal Pradesh Hima Urja only, and depending upon that, they can attract investors to come and prepare a detailed feasibility report. So this is 4 seasons we thought is autumn, winter, summer, and monsoon. We thought that we can give a runoff estimate and power potential in these 4 seasons. So you can look into that paper, Kulkarni et al. 2002 paper is there, and maybe Arya can send you that paper. So the model was set up, is a much simpler setup with a certain idea. Idea in this is a small hydropower, small basin. That means the basin which is has 1 or 2 glaciers, and it is a micro or mini hydropower station. It is not very large hydropower, large basin. So there is not significant change in the spatial variability in the parameter. In addition to that, there are, because it is a small, all parameters can be taken as a lump model rather than it is a spatially distributed model. So it is fundamentally this is using temperature index, which is a model setup is such that it starts running from winter because that is where fresh precipitation has taken place. And it is in a glaciated terrain. It means there is not much forest cover. And idea is that the interference because of forest is minimum and there is very little infiltration into the ground. And because of there is no vegetation cover, so there is also very little evapotranspiration. So with these conditionalities, this model is written that average is seasonal runoff. So what use Q, which is the average seasonal runoff, it depends upon runoff coefficient. It is then melt factor, temperature, then area of snow and glacier, area of seasonal snow, water equivalent of winter snowfall, winter snowmelt, and these are the parameters. You will work in that, and you will. So it has basically though two component. One component, it uses the runoff from seasonal snow. It uses the runoff from glaciers, and it estimates the runoff from the land because of rain, which is not covered by snow and glacier. That's the idea in this model. So these models was written. The first thing we need to know is how much, where are the limits of this season? That means it is easier to trace the season, because remember one thing, that most of the runoff data in Himalayas or in India, if you go to the any CWC or Bhakra Bias Management Board or any other thing, they will give you runoff data, mean runoff data of 10 years. So you need to work on, they call it the 10 really data. So you can use it, that data. So, so by using hydrograph, what we did is we estimate December to March 20 is the winter, then March 20 to July 10 is the summer, then July 11 to September 10 is the monsoon, and September 11 to November 30 is the autumn. This is a mean value. That is, the monsoon is going to change a little bit here and there, give and take 15, 20 days here and there. But these are the ideas. These were used. Remember, these limits of seasons are done in a Satluj River basin, including Beas and Satluj, which is Indian part. If you go into the Karakoram, these figures are going to change. If you go to Chenab, these figures are likely to change. So you have to really critically analyze the hydrograph to understand how to put the limit, so that what is the phi which is necessary to capture the season correctly, because there are different ways by which runoff is estimated. If you really look in terms of monsoon, it is predominantly coming because of the rain. And if you come to the summer, it is predominantly coming from significant melting of the seasonal snow. So that is why it is important for us to address this issue. Then there is, you can take either, since it is only to estimate a long-term change, it is not going to get 10, how it is varying each 10 days, it is going to take season, and it is averages over a period of 10 years, 20 years. Therefore, you require the average seasonal rainfall and average winter snowfall. If you have a data of that region, you can take it, because now there are so many observatories. When we were developing this model in 1990s, there were hardly any observatories, but now there are a lot of observatories, and as well as there is also reanalysis data is available. So you can use that data and get the average seasonal. If you want to work on a decadal scale, that means how runoff will be this decade and how it will change in next decade, because of the climate change ideas, then probably you can set up this data input in a slightly different fashion. So this is what you can do. Then there's the melt factor. What will be the glacier melt factor is the glaciers, glacier altitude in summer, snow melt in monsoon, melt factor in autumn and winter. So these are the different melt factor, and then there is the idea of runoff coefficient. That means how much you have generated and how much it has come into the runoff, into the stream. So it is not necessary that whatever you have melted, 100% will come into runoff. So some of that will get, so it depends upon the soil moisture condition and terrain condition. So it can be 60% to 80% will come depending upon monsoon, since it is most of the soil is at the field capacity, and because of that huge amount of water will come. As summer comes, it will start reducing. And as glacier comes, it is still reduced, essentially because there's a lot of whatever made on the surface, it takes a lot of time to get transported, or it internally consumed by glacier to change its, to change the temperature of glacier, as well as there's the internal storage also inside the glacier. so it has relatively less. So these models were basically originally developed at Malana Nala, and then there is a Tosh Nala where they were tested, and then we were associated with this model when Himurja applied. We called their engineers to come to Ahmedabad. We trained them, and we have done for Sorangad, Vangargad, Kirangad. And after that, this model was completely installed in electricity board and Himurja's computer, and we have really withdrawn from this effort. Around 2006 and 7 time frame, we withdrawn from this effort. So this model is developed. You will actually work on this model subsequently. Therefore, I will not go into the much more detail. You can have a detailed discussion with Tejal and other people who are going to work, talk to you on this model. So how much is, you can see here, this error, when it was developed at Mala, error was from 2% to 3%. Winter was very good, and then summer was a little bit higher, and monsoon was much more higher. So you have to realize what really happens in this model. We can now do it much a decent job than what was done at that time because of the lack of satellite data. So this was validated in Tosh Nalan, where error is also within the 10%, except for monsoon time, which is very high, and we did not give much attention to that because monsoon was not on the radar of electricity board. And so you can see here that from whatever area you use, they are giving very good result in autumn, winter, and summer, except in monsoon, where runoff is predominantly coming from rainfall rather than in their contract thermally, because this model is all about temperature and conversion of temperature index into the runoff. So it is much more error when it comes to the monsoon time, but it is giving reasonably good result when snow and glacier melt is contributing significantly higher. You can also convert that model runoff, field observed runoff, and you can also do it power potential. Probably you will do it now that the simple universal equation is there, which equation, power equation you can use and convert this runoff, if you know the head, into the power potential. So each stream for different season, we can estimate the power potential. So that is the idea of this model.